So we've looked at so far a single main effect that was continuous variable between 0 and 1. Another type of covariates which we might have is categorical one. That's not found. I created this categorical variable somewhere at the beginning that I didn't run. Yes, it's right here. So we say if the dominant habitat is deciduous, what we just calculated before, say it's 1, otherwise 0. Okay. So now if I print the counts versus deciduous or not, this is what I see. I get the higher counts in the deciduous environments, but still in non-deciduous, which means it might be a mixed wood or more of a coniferous. You still get some Avambers there, but more often is the deciduous area. And I'm not saying this is the best way of coming up with a predictor like this. I'm just using it as an example because we already know what to expect for the deciduous trees. So if I scroll back down to here, after GAMS, we were looking at categorical variables. So what I wanted to show you is if you take a categorical variable, that is going to translate into this so-called model matrix. So before, we had this, some amount between 0 and 1. And if you notice, these are the names for our coefficients. So really, this is the matrix that gets multiplied together with the coefficients when we are making a prediction. And the way to think about a categorical covariate is it becomes 0 or 1 when it is deciduous and it is not, and it just becomes the same calculation. You take the coefficient and each row, these numbers get multiplied together. So if you take the coefficient for the intercept multiplied by 1, that's the beta naught term, if you recall. This one becomes coefficient times 0.85. That's x1i times beta 1. And if you have a categorical variable, that just becomes intercept plus beta 1, or intercept and nothing. So this is, if you have multiple levels, then the first level, like here, the non-deciduous, is going to be the intercept. And then if you have more levels, that's just going to be like extra columns added with this dummy coding of 0 and 1. When the label is that, you get a 1, otherwise a 0. So this is how you think about categorical variables when you try to make a prediction. Let's fit a model like that. Summary, again, we see it is important, but we don't see as high of an effect size as before because we're kind of lumping it together and treating it just as a single state instead of this linear relationship. And now we can also visualize kind of how this cut happened with deciduous and the categorical counterpart. So what if we want to fit a model with all the levels, which is HAB, that has deciduous and non-deciduous? Now we have all kinds of land cover types, but you see only the deciduous effect is significant, which means the rest is just really, you get an effect size, but whether it's still 0 or not, you can't really tell. but when it is deciduous, you see this effect quite clearly. So as a general way of getting the prediction is to get the coefficients, get this model matrix. So if you want the model matrix for this model that we just did, which is called MP3, and it's going to be huge. So let's just do the top part of it. Oh, this should be a data frame like X. Then this is what we get. So the coefficients MP3 are going to relate to these columns. So we code the whole data as intercept, and whenever it's deciduous, you get a 1. When it's open wet, you get a 1 here, and so on, and multiply together with these coefficients. So once you have the coefficients and this model matrix, you multiply them together using this matrix product notation and exponentiate. And the reason I'm going this deep into the prediction is we are going to use something called offsets, and prediction with offsets in GLM is really tricky, and you will see why we want to control what the prediction is doing. So let's keep this multiple main effects. Feel free to run it on your own time, and then interactions. When we look at interactions, that means we have these two terms, say x1 and x2, but also not just their main effect, but also their interaction, which is this column in the coefficients. And that translates to a model matrix. Now imagine you have the coefficients for the intercept, term 1, term 2, and their interaction. What that really means is that you multiply together x1 and x2. So you have beta naught, beta 1, beta 2, and beta 1, 2. So now you take these values, 1 times beta naught plus 1 times x1 plus 10 times x2 plus 1 times 10 times beta 1, 2, right? So you need to multiply together the two x's and apply the coefficient. This is how we interpret an interaction between two linear terms. And if you have an interaction between a categorical variable and a linear one, that just means you get an interaction for all the levels of that discrete covariate. So it becomes a bit more complicated to think about, but really what it comes down to is this model matrix in the background and kind of simple addition and multiplication. So let's do the real data analysis to get another model. And if you run up to this point, then you're going to have this many models with 1, 2 covariates, discrete, continuous, their interaction or not, and you'll be able to see which one is the best. But I haven't run all of those, so I just leave it up to you to finish this if you want to see which one of these really simple models is going to be the best. If you still feel that Poisson is not the best choice for an error distribution because the data seems to be more dispersed, you get a lot more zeros, which is partly due to we have detection error, and that's why we have that many zero observations, even though the species might have been there. Or maybe just those 6s are really rare and you wouldn't expect them too often. So in this chapter, if you run it, you will be able to see how to use a negative binomial model, which has the same model for the mean. So the same link function, same everything. What it is different is that the variance is a different function of the mean. So you are allowed to have more or less variation as the mean is changing. And that's what that extra theta parameter is controlling there. If you have excess zeros, which we often have, then you can think about the zero inflated Poisson or zero inflated negative binomial model. And these are just examples from the PSCL package, which gave me, by the way, lots of inspiration for detect. And then you can also use AIC to see which one might be best. And as I recall, if you run it up to this point, you're going to see that the zero inflated Poisson is going to be the best fit. You can also have a look at mixed models. And here we have the site ID. At the same site, we collected multiple points around that area. So you can take that, site ID is like individual random effect. And then the next one is the study area, which is more that cluster of points. You can then have a look at these. This deals with any kind of unexplained variation that is not part of this fixed effect component. And this is more kind of capturing that these clusters of sites should be more similar to each other because there might be a hotspot for that species or for whatever reason. And if you run this piece again, you're going to find that this clustered model with random effects is going to be the best. So then we can think about why that is the best model, what kind of mechanisms might lead to such random effects and how we are going to interpret that or making predictions for those. So we'll come back to these GLM models at the end on day 4, once we've covered how do we estimate what the nuisance parameter, which is just something we need to know to account for those, but that's not the real interest. Our real interest is still going to be population size, abundance, and changes in space and time. So now if we go back to the original question of when we combine together different data sets, and this JOSEM data was collected in one way. Now if you look at another data set in the next province, which was collected with a different protocol, how do we combine these together? Because we saw that methodological effects can be huge. So let's now pretend that we have different count and duration effects. So what we can do here is create another cross tab, site ID, and duration, which, as you recall, 3 to 5, 5 to 10 minutes. So it's different count duration. So if we do that using a 3-way table, then we can say for Ovenbird, this is what the table is going to look like. Sites, and then the different time intervals. So where I'm getting to is, let's pretend that we have the data collected with a 0 to 3 minute protocol, or 0 to 5 or 0 to 10. Will that have an effect? So we still have SPP set as Ovenbird, so we can get the matrix Y this way. And you can see that the column means are going to be 0.67, plus in the next bin, you have this value plus this value. So you see the differences. One refers to 3 minutes, then 2 minutes, then the extra 5 minutes. So what we're trying to do next is let's create 3 responses. One where we are just looking at 0 to 3. The next one, add up the 0, 3, and 3 to 5 so that it covers 5 minutes. And then the third one is going to be 10 minutes. You can see under 3 minutes We have slightly more zeros, but definitely a lot less of these high counts. And as the time is spent surveying the birds increases, then you see all these counts to increase slightly, which means method is really having an effect on the intercept term. So this is the count distribution over 3, 5, and 10 minutes. You see how the zeros are getting fewer and higher counts are getting higher as you spend more time. So all these non-detections are turning into some form of detection here because you just spend more time and there were more chances for that bird to get detected or just vocalizing during the time that you spend there. So we can fit now 3 models to the same data. So we know the real bird abundance was the same, but your observations changed depending on what protocol you used. Now, all of a sudden, we have different fitted means. And this difference can be quite huge. So it's like 20–30% increase just based on 10-minute versus 3. So now if you want to combine these different methodologies, then you really need to take a look at those methods and somehow try to harmonize or account for these. Another way, which I'm not going to explain in details, but just instead of looking at the same data set under different protocols, now we pretend that parts of the JOSM data was collected under A, B, and C protocol, which is 3, 5, 10 minutes. And we're just going to make up a random subset. Once you do that, you can see that there is clearly a method effect. So I'm not throwing in any deciduous forest or any kind of predictor, just I know it's method A, B, or C. And you see clearly that as the time spent surveying increases, you get different means. And what I did here, I dropped the intercept so that by looking at the coefficients, we get the estimates immediately without any kind of post-processing. So now if we include deciduous plus method, maybe that's a way of correcting for these effects. So one can do, I know it's protocol A, B, and C. Let's just use it as a discrete variable and hope that things are going to turn out well. I think that's a good way of approaching things if your goal is only to account for the differences. But you need to know something else if you really want to make sure that whatever you're estimating is going to be your measure of interest. In this case, not just relative abundance, but absolute abundance. So if you're okay with relative abundance, maybe having methodological details as part of the fixed effects is going to take care of it. Not always, but could work. So this is for time. And there's also sampling area, which, as you recall, is probably going to have more impact than time, although time was big enough. So now we can do the same with a count radius, and I'm going to just say 0 to 50 and 0 to 100. We are not going to deal with unlimited counts, and I'll explain later why. So there we don't really know what area we are sampling effectively, and there's a way to estimate that, but we haven't covered that today. So on day 3, we'll come back to unlimited distance counts. Right now, we have these 2 areas that we sampled, and again, we pretend that some of that is, sorry, here we have 50 and 100 side by side, just to look at the effects. But the same idea applies. We can combine these different methodologies together and account for the differences. So you can see here that these counts again differ quite substantially. And if you look at this similar graph, you see the same pattern. You're going to get less zeros, more high counts as your area increases. As a result, you can expect this is going to show up in a fixed effect, or it is going to kind of bias the intercept depending on how much A versus B you are going to have. So you see, intercept is quite heavily impacted by the area surveyed, and there is also a slight difference when it comes to the deciduous effect. So what can we do to resolve this? And we only have 10 minutes left, but this is going to quickly lead to what QPAD means and what we are trying to achieve in the next 3 days. And the only concept we need to cover today is an offset. What does it mean to have an offset in our models? It means that you have a known component. And by known, I mean you know its value, and you assume that the coefficient for it is 1. So you can include it as beta naught plus beta 1 times x1 plus offset. So that is just going to offset your expected value, higher or lower. So again, this is on the log scale, so you need to think about the transformation. But on the log scale, this is just something you add or subtract from the mean. So if you have more area to sample, like twice as much, then you might say, I expect twice as many individuals. So with area, this linear relationship is something we would expect. If I survey half the area, I would get half of the individuals because density is still the same. So if you know this relationship, then an offset can be a really good way of incorporating this known fact into the model. So we have here the 50 and the 100 meter. I've already done this without the offset. Now what we are doing here is see, we specify an offset term. So just repeat log of 0.5 squared times pi. So this relates to the 50 meter, but 50 divided by 100, so that we can talk about area in hectares. So what this means, this is my area based on the known distance, 50 meters squared times pi. We take the log and repeat it as many times as the number of rows in our X table. And we have deciduous as a fixed effect, plus this offset. The next one, when we have 100 meter radius surveyed, then we say, now we take the counts from the 100 meter survey, same fixed effects, but now we have the area as 1 squared times pi, which is pi, and 1 because 100 divided by 100 is 1. So that's 100 meter radius. Repeated the same way. So we hope that this is going to take care of everything. Almost. So if you see the mean prediction, it is much closer than it used to be. So if you look at 0.29 versus 0.78, that's a lot more different than 0.37 and 0.25. So you're getting somewhere. This offset and with the known area survey, that is really helpful, although it is not making things exactly the same. And you might wonder why that is the case. And on day 3, we are going to get the answer when we cover distance sampling. As the area increases, detectability is going to change with it, because the farther something is, harder it gets to detect it, because we can't see, can't hear that far very well. So established now that there are these methodological effects, and We can use it as a fixed effect or as an offset, but it looks like it's not perfectly solving the issues. So is there something clever that we can do, given that we have this bird data and we have the textual information, which time and distance band the individual was detected in? So this is that ancillary information we are going to rely on during the next 2 days. One aspect is time. So how to utilize that information, that is the first 3, the next 2, and so on minutes, and how to utilize the information that it's coming from different distances from the observer, and how we can estimate these things. So that brings us to this outlook for QPAD and what QPAD really means. So we are trying to estimate n, and there is no detection error involved. Then we can say abundance is really just area times density. And if we go out and this is exactly what we can sample, then there's nothing else left to do. Our observation, which is y, we model its expected value, that should equal abundance. In reality, what we see is what we observe relates to density times area, but there's also this unknown C factor that we need to estimate. Once we can estimate that, then we know D times A, and as a result, we can talk about N. So we are going to expand this C into 2 components. One is going to be P that relates to if a species is there, how likely it is that it will show some kind of behavior through which it becomes available for me to detect it. It vocalizes, it moves so that I can spot it. The other one is, I call it Q. Once it made a move or vocalized, I, as the observer, depending on how far I am from the bird, will I be able to detect it? Once I know these 2, then I can put things together, and this is the equation where QPAD is coming from. So density times area times probability of availability times probability of detection is the count that we observe. If we can estimate P and Q and sometimes A, then we will know D, so we can talk about density and as a result population size and abundance. So if you slightly reorganize this into QPAD, that's the acronym we are using. So now you know what QPAD means, and the only thing left to do is to figure out ways of estimating P, which is Thursday, and Q, which is a week from now. And then on day 4, bringing it all together and see how we can use these estimates as offsets and plug into GLMs or other kinds of models so that we can account for these differences a lot more meaningfully than just fixed effects or these naive area-based offsets. One last thing, I'm scrolling up here, and sorry that I bothered you with matrix products and model matrices and coefficients, but why that's really important is because of this. If I just fit some model, include offset in different ways, so you can either say it's an argument or part of the model formula. Something. Oh, I don't have log A. Okay, I skipped too much, but just to finish, what you should expect here if you run all the code chunks is that the prediction seems to include the offset. And our point is to include the offset so that we can account for these differences. But then when we make a prediction, we don't want an offset because it is going to be fine enough. That's the correction part. So if we are interested in density, we want to account for C, but we don't want C to be part of the prediction because we are not interested in our counts. We already observed that. We are interested in N that we haven't observed. And if our prediction is going to incorporate these nuisance factors, that is not really helpful. And the way to get rid of the offset is to making sure that it's not part of the prediction. And with GLM and the standard way of working with these predictions, as in here with the fitted function and predict function, that is going to include an offset. And you need to find a way to set that to 0 or just do prediction like this. Model matrix times coefficient. And if you exponentiate and add the offset, then you get the offset. If you omit the offset, then you don't get the offset. And this is what we want when we make a prediction, because this is going to tell us density per unit area without any reference to methodology. So that's where I close today. Thanks for enduring this really long session about a GLM recap, but this is going to be a great place to start the day after tomorrow to talk about what the birds are actually doing and how we can utilize that information, that is, what is the time of detection, to talk more meaningfully about one part of this unknown C parameter here. If you would like to go over these chunks, things that we skipped, feel free to do that. And so if you have time, you can think about why should we care about this C and why relative abundance is not enough. Why do we want these absolute numbers? Because otherwise, if relative abundance is all what you need, then you probably don't go very far. Whereas if you need absolute numbers, then certainly there are things you have to do. But why should you care? This is a question I'm asking, not that I know all the answers, but I'm interested in hearing your opinions about this.